Okay, great. At the end of yesterday, I had started to introduce some experiments we're doing with atoms and photons that mediate on.
I think you cut out, and I don't think I'm the only one.
No, she's frozen. At the end of class, I had said, let's can apply that program of some toy models.
Take a minute for her to hear us.
Yeah.
We lost her.
We lost her. Okay. Oh.
I'm sorry about that glitch. I don't know what happened or why I suddenly have a Stanford background instead of the other one.
You froze up. It was fine until you started to lecture, and then basically the moment you started to lecture, you froze. So
yeah, so I hope that doesn't happen again. Let's see here. Okay, so
just take it from the top.
We will take it from the top. So let's get this screen shared. Can you see my screen?
Yes.
Awesome. Okay. So yeah. Okay. So I was showing you the system where we can program the graph of interactions between cold atoms. And I said we wanted to now see whether we can apply this to maybe build some toy model inspired by ideas from quantum gravity. As an experimentalist, I have definitely relied on interactions with theorists in order to sort of think about what would be interesting to do in the lab. And so what I'll talk about now is something that was inspired by a really wonderful collaboration with Steve Gubser at Princeton. Steve, as you may know, sadly passed away in a climbing accident a couple of years ago. But I was really fortunate to get to interact with him over a couple of years and to learn about a sort of version of the ADS-CFT correspondence that he formulated, which is a little bit different from the standard version. And it's kind of inspired by the question of what is the, and this is actually a direct quote from Steve, what mathematics is behind the reality, which we experience as smooth space-time, but which in all likelihood is discrete at a fundamental level. And that's sort of inspired by this idea of the Planck length as the shortest length scale. And Steve had actually formulated a version of the ADS-CFT correspondence where there's a sort of a tree graph, which you can think of as a discretized model of a space with negative curvature. And speaking, kind of to see why that might be the case, if you kind of think of, as having this sort of a binary tree, and I have like my physical system consists of n sites along the base of the tree, the depth of the tree is only logarithmic in that size, right? And so there must be some, if I sort of wrap this around and think of it with periodic boundary conditions, I have something where the radius is only logarithmic in the circumference, and so there must be curvature, right? And so that's kind of, this is some sort of a discretized version of a curved space. And so this is something where again, the physical system lives here on the boundary, but there's sort of a way of kind of visualizing the bulk geometry in terms of this tree graph. Okay, and so we'll say a little bit more about that in a moment. But so can you build things that look like this in the lab? One thing that's worth pointing out, there are actually some people working with systems of superconducting resonators, which they actually kind of can wire up into like hyperbolic geometries and things like these sort of tree graphs as well. So that's kind of actually one approach people are taking in the lab to kind of realize maybe some kind of effective curved geometry. What we would like to do is a little bit different, though. We would like to not like literally sort of build this tree graph, but ask, can we realize a system that has this property that, again, the physical system, sort of the leaves of the tree, but there's some kind of a bulk that emerges as a natural description of the quantum correlations in the physical system. Okay, so there's a toy model that we had written down kind of on paper a couple of years ago, where the basic idea, and this was actually originally motivated by thinking about how one might build a fast scrambler. So how one might actually build a system where information can spread very quickly from one site to any other. And the basic idea was if you have this programmability that we have of interactions, we didn't have it yet, but now we do. You could imagine, say, building a system where in order to allow information to spread very quickly from one site to any other, I might build in couplings between nearest neighbors, second neighbors, fourth neighbors, eighth neighbors. So I have couplings at sort of lots of different length scales, powers of 2, so that it would sort of very, very efficiently be able to kind of get from one site to any other. So that's the general concept, but now there's an ingredient that actually Steve added to this model, which is, let's say there's also a power law exponent S. And if S is negative, that means interactions, they're at these sort of special distances, but they decay with physical distance. And in that case, this would look not too different from a linear spin chain. The nearest neighbor interactions would dominate. But there's another limit where actually, if you had this model and the interactions grow with distance, so that's kind of weird, it's sort of a weird model physically. Interactions are sort of only at these powers of 2 and they grow with distance. Then the correct way to think of that is, and I'll try to convince you of this in a moment, is to think of the sites as leaves on a tree where the tree captures something about an effective distance between the sites. Roughly speaking, you can think of this as this is something where even sites and odd sites are the most weakly connected. And so the left and right half of the tree represent the even and the odd sites, and so forth. So that's kind of, so the claim is that then one should be able to build something that looks like this tree graph that's sort of like a discretized version of a hyperbolic space. And in between these two limits, these are two very different geometries. In between these two limits, the conjecture is that this system could be a fast scrambler where kind of everything is strongly connected to everything, and information can spread very quickly across all degrees of freedom. So we decided, well, we have this toolbox now for sort of programming the graph of interactions. Let's see what happens if we try to build the model that we think should act like this funny tree graph. And so again, in the lab, we can just do that. We can say we'll turn on interactions that are non-zero only at distances that are powers of 2, and we'll design them so that they grow with distance. And if you then measure, remember, we basically have this system where we can measure correlations between the magnetization on site I and the magnetization on site J. And if you look at the correlation versus distance, it has some weird non-monotonic behavior if I plot this versus like the physical distance in the lab in my chain of, in this case, 16 sets. Okay, but if we have correctly realized sort of this new geometry, there's a way that we should be able to kind of rearrange these sites in a way that these measurements will start to sort of look more ordered. And the basic idea is that the way that this tree is constructed is to say, I have the weakest interactions in this model are between, again, even and odd sites. And so the first thing I should do is look at the least significant bit of the site number in my spin chain and go left on the tree or right on the tree, depending on that bit. Okay, and then I'll go to increasingly more significant bits, and again go left or right depending on that bit. And so basically, again, because we first look at the least significant bit, what I should do in order to determine sort of the position of a physical site in this tree graph is I should reverse the order of the bits. Does that make sense? Right? So the left half and the right half are ones with 0, 1 as the least significant bit, and so forth. Okay, and so there's kind of a rearranged order of the physical sites compared to the sites on the tree. We think, right? So if we've correctly realized this tree graph, what we can do is we can plot the correlations as a function of this map between the ordering in the physical space and on the tree is called the monomap. If we rearrange sort of the sites according to that map, and we look at this correlation plot again, it starts to look a sort of clearer structure, and you'll start to even see some blocks showing up. So these are just the experimental data that kind of indicate something about the hierarchical nature of this model, right? So there are these large blocks that have to do with are the sites on the same half of the tree, and then blocks of 4 and blocks of 2 are a little bit harder to see. There's just finite statistics in our experimental data, but you really start to see this hierarchical structure emerging. You can also now ask the question, what if I now actually plot correlations versus the correct measure of distance on this tree? And the correct measure of distance is essentially set by how many levels do you need to go up in the tree to get from site I to site J. That's actually the log of the negative log of the distance. So if you need to go far up the tree, that's a long distance. If you just need to go up sort of one leg, that's a short distance. And if we plot these correlations versus the tree distance, you see kind of a smooth decay versus distance on the tree. That kind of matches the idea that what we've realized is this effectively actually very different type of a geometry. So we can take this one step further and ask, if you remember last time, I took sort of our measured data and I was able to kind of reconstruct an effective geometry, like let's say a Mobius strip, based on the spin correlations. So here, the tree is different from the Mobius strip, right? Only the leaves of the tree are actually physical sites. But so I kind of asked my students, well, can you think of a way to still do some kind of like reconstruction of the geometry, including this bulk geometry that's the tree? And so the idea they had was, well, let's start with what we did before, which is to look at the correlations between these sites in our physical system and use them to find the best fit embedding of the sites. In this case, we decided in 2 dimensions to explain the correlations that we measure. Okay, and so in this case, I'm plotting here 2 examples, one actually where the interactions decay with distances, and this is sort of more of a linear spin chain, and one where the interactions grow with distances, s equals +1. This is the thing that should look like a tree. So again, the first thing we're doing is just saying, based on the measured correlations between the sites, what is the best fit embedding of the sites in some 2-dimensional space? But then we're going to ask, let's now adopt some kind of a coarse graining procedure where we draw bonds between sites whose spins are strongly correlated. And we'll repeat that procedure until we'll then treat those as a larger site and repeat that procedure until everything is connected. So in the case where we had just this spin chain with periodic boundary conditions, the strongest connections, this sort of most strongly correlated spins, were nearest neighbors. And you connect everything to its nearest neighbor and the whole chain is connected and you're done. And this kind of looks trivial. But in the case where we have this, what we think should be a tree, we draw these bonds, again, at sort of the distances where the correlations are strongest, treat those as larger sites and draw new bonds. And in fact, those bonds precisely give rise to this tree graph. And so this is something where just by doing this kind of a coarse graining procedure on the measured data, we really can start to kind of visualize this bulk geometry that captures something about the structure of the correlations in the physical system that lives on the boundary. Let me pause there and just ask whether there are questions in what I said so far. No questions.
Just one curiosity. This is all for fixed time slice, right? So no time evolution here.
Yes. So in the experiment, we initialize some simple state, simple product state, and we evolve for, in this case, a fixed time We have looked at different times, but essentially for everything I'm showing you here, we evolve for a fixed time and then we perform a measurement. Yes.
Okay, thank you.
Yeah.
Hi. I have a question.
Yeah.
I'm a bit confused about what you're trying to achieve with these experiments. Like, we have no problem understanding the dynamics of a system of 16 qubits or what these are.
Yeah, and so these
Well-
are things that we can calculate.
Right.
So the goal ultimately is kind of to get into a regime where you can't calculate things. But usually we like to sort of in the lab develop a toolbox and test it in a regime where there are still things you can calculate, right?
So the goal
yeah.
is to scale it up to a level where with current technology, we aren't able to do the calculation.
Well, I think I mean, so yeah, so to my mind, part of the idea here was to start to get a sense of like, what are the experimental protocols you might want to use? Let's say you have a system. In this case, we had a toy model where we kind of know. It wasn't actually obvious to me, but we knew, from thinking about this model for a while, that there should be a way to think of this in terms of this graph that represents kind of a bulk geometry for the system. It would be really great to be able to have a system where you don't know whether there is such a picture, but maybe to have a protocol for just like doing an experiment and discovering that, right? And so I would say for sort of in the lab, we kind of need to start by building up, first of all, the tools in a place where we know what should happen, so that we can sort of test whether the tools are working, even in terms of the control of the interactions. And then also that's a good place for starting to kind of develop some ideas of sort of what are measurement techniques that you might want to apply to the system.
I guess my question was just, what could this potentially tell us about gravity, and if anything?
Well,
Like
I
even
think,
if we
I mean,
scale
I
it
think
up-
this would be a fun thing to discuss more also in the Q&A. But one of the things I'm curious about is kind of, could we, again, we started from a toy model where we thought that there should be a nice picture for this bulk geometry as kind of a tree, right? But could we take this type of a technique and apply it in a setting where, again, where we can't calculate what will happen, but we can do a measurement that kind of reveals some kind of a geometrical way of thinking about the structure, the correlations in the quantum system. So for me, this is partly, I will say, I kind of yesterday already said a little bit, there are motivations from two sides. One of them for me is actually taking ideas from gravity to actually understand quantum systems. And the other one is maybe understanding something about gravity. The second one, I would say, I'm not in the best position to immediately tell you kind of what we should do to understand gravity better, because I don't spend most of my time thinking about gravity. I spend more of my time thinking about quantum mechanics. But to me, this is actually really kind of a nice insight for how one should even think about quantum systems. But I would also love to know, is there something one could do, that would, I think so to me, it's also kind of an illustration of this idea of geometry kind of emerging from entanglement. And so is that, how broad is that concept? Is that applicable to our universe? I don't know, right? Maybe this doesn't tell us that, but it gives us sort of a playground for starting to explore that idea. I saw somebody unmute them, unhide themselves. So was there another question? Or a follow-up to the current question? I mean, it's a really good question, like what exactly can we learn? And I think just starting to even build a toolbox and kind of even just like for me to learn the language of another community and vice versa, I actually think is kind of where you have to start, right? In order to be able to connect experiments with your theory. So.
All right, thank you. That helps.
Yeah. Okay, yeah. And so again, maybe this sort of came off as seeming obvious because we programmed in a structure that we thought should have this kind of tree graph as the best description of the correlations. But first of all, that wasn't actually obvious when we first wrote down this Hamiltonian. And second of all, there are cases where you might not know what you're looking for. And the hope is that then you could still do some kind of a reconstruction like this. Great, okay. And lastly, I think this highlights kind of the ability to realize exotic models that are just different from, let's say, local spin chains. And so this is really a completely different notion of geometry that's in terms of the type of a metric in this system where distance is described by this tree graph, something called a non-Archimedean geometry, that it's not something that you would think you can, it's something you might not think you can build, but with the control over the interactions, you can approximate or simulate that. Okay, great. So then I'll just take one step further and say one kind of additional thing you can ask is now, as I tune between these limits of the simple, right, we have these two radically different geometries, as we tune between them, we can ask kind of what happens. And in two halves, right? A physical geometry, which is just one-dimensional.
Monika, you froze a little bit. Maybe for 30 seconds.
Oh gosh, okay. Unfortunately, the connectivity in this room is not as good as I had hoped, so I apologize for that. Can you hear me again?
We
Yes.
can hear you now.
Yeah.
Maybe try toggling your video off to conserve bandwidth.
Yeah. Okay. So you can still hear me?
Yes.
Okay. So lastly, we said, what happens if we kind of tune between these two limits, right? We have these very different geometries. What happens in between them? And the thing you can do is just say, I'm going to cut the system into two halves according to either the physical geometry, right? Cut it in the middle of that 1D chain, or according. And we'll ask sort of how strongly correlated are the two halves. And in this case, we're using a very coarse measure, which is essentially asking literally treat that system, that half of the system as a larger site and ask about the correlations between the total spin on those larger sites. So if we cut according to kind of the physical geometry, we literally cut that 1D system in half in our data analysis, then as a function of this parameter S that tunes between the two geometries, we see that if S is less than 1, which means interactions decay with physical distance. Can you still hear me?
You fell out again.
Okay. I will fix this by tomorrow, but unfortunately, this is what we have today.
Yeah, and
hear
then
me,
on
but
the
you
chat,
can't see
if you got your video running and you're an observer, switch it off. Okay.
Yeah. So you can see my slide?
Yeah, we're fine.
Yeah.
What I
Okay,
asked
it's
was
unfortunate that I can't see your faces, but I guess that's where we stand right now. So, okay, let me keep talking through the slide and then maybe we'll pause and see whether we can fix anything. So, good. So again, so when this exponent is less than 1, so and we cut according to the physical geometry, then that's where sort of the correlations between the two halves are weakest. And not too surprisingly, if we have this very non-local model where interactions grow with distance and we cut according to the physical geometry, between the two halves are still quite strong. So if we flip this around and we cut according to the tree, we see that these correlations are smallest if we in fact have kind of the tree-like geometry, so that makes sense. But you can also ask the question, let me consider all possible ways of partitioning the system into two halves. And how strong are the correlations between those halves? Let me take just the optimum way of cutting them that minimizes the correlations. And even for sort of that optimal cut, if I look at the central point at S equals 0, where interactions have the same strength at all distances, there's essentially no way of cutting the system so that the correlations between the two halves are small. So this is kind of tuned between these two radically different geometries. There's a point in the middle where everything is strongly connected to everything. And that is the point that appears to be conducive to this fast scrambling behavior. So the model is, there's no way of thinking about the system in which it is local, neither in kind of the physical space or on the tree. Everything is strongly connected to everything, and it's just a highly non-local graph. So that, I'll just sort of mention when we were first thinking about this toy model, we kind of, as somebody said, these are things that you can calculate either in a chain of 16 spins or alternatively also in kind of semi-classical limits. There are various ways you can analyze this. If you take the chain of 16 spins, the natural question you would really want to ask about is entanglement, right? Sort of in those calculations, there was a very similar behavior in sort of the entanglement between two halves of the system, peaking at this special point s equals 0, where interactions have the same strength irrespective of which power of 2 distance you're at. And so again, this is kind of an indication that this could be a situation that is conducive to fast scrambling. Two kind of points I want to make about this. One is it would be wonderful to be able to directly measure entanglement in experiments, and that's actually something that can be done, and that I'll say something about next time. That said, actually, are kind of simpler, much simpler proxy measurements. Sometimes in an experiment, it's useful to just ask what is the simplest thing we can measure that already sort of shows the essential physics. And that already starts to show us that there's a regime where there's really kind of no sense of locality in this model.
Can I ask a quick question?
Yeah, please. Yeah.
On the previous slide, I just was having trouble visualizing what you meant by, I mean, I can see the pictures like the tree cut and just the standard cut, but I wasn't, or the physical cut, I wasn't sure how like the physical cut would look in the tree picture and vice versa.
Oh, yeah. So that's great. So the physical cut in the tree picture, I almost wish I could zoom into this picture, which is not so easy. But basically, I would actually be cutting like pairs that are linked.
Okay.
Sites apart physically.
Right.
And those would actually be separated by the physical cut. Like, so here, these are sites 1 and 9. Those are on opposite sides of the physical cut. So we would basically be cutting precisely where we drew those bonds, saying those are the sites that are most strongly correlated. All of those would be, so, and so in that sense, the physical cut is bad if you have the tree-like graph of interactions.
Got it. Makes a lot of sense.
And so that's, in some sense, and that's not surprising because the whole way we reconstructed kind of this graph here from the data was looking where the correlations are strongest. And yeah, so the fact that kind of this last bond is the tree cut is right across this last bond is saying the tree cut is the one that will give you sort of weak correlations between the two halves,
right?
If you have the tree-like model. And so another way of saying that this is just sort of a way of probing, is there any sense, or like, is this the right way of thinking about the geometry of the system, right? Is this cut local, given the graph of interactions I've made? And the point is sort of at s equals 0, where I have neither the linear chain nor the tree, there's no sense in which you're making a local cut.
Makes sense. Okay, thank you.
Okay, other questions? Okay. So yeah, so okay, so then the idea is at that point where sort of everything is strongly connected to everything, that looks conducive to fast scrambling, as was pointed out before, sort of you can do calculations in a system of 16 sites, or if you work very hard, as some years did, even 64 sites for a spin half quantum system. But if you want to say something about sort of whether the time for information to scramble is logarithmic in system size, you'd really want to be able to scale things to kind of large systems. And the closest that we could do in terms of sort of analyzing this model, doing some kind of a semi-classical model where you think about sort of large spins and treat them semi-classically. And in that kind of a model, one can, well, first of all, actually, there are sort of two things you can ask. One is if I have a single excitation in a quantum model, kind of how long does it take for for sort of correlations between a site that I excite and other sites to spread across the system. And there, if one sort of looks at kind of correlations versus there's kind of a slightly funny looking behavior where there's aspects of this power of 2 structure of the interactions that lets you see sort of stripes versus distance. But roughly speaking, kind of there's some evidence that the characteristic time for correlations to spread behaves logarithmically. And one can see it more clearly if you say, I'm going to rearrange the sites according to just distance on the coupling graph. So this is again S equals 0. The longest distance, because we have interactions at powers of 2, is at something that scales logarithmically in the size and in the number of sites. And so sort of as a function of distance in the coupling graph, it takes a time linear in that graph distance for correlations to spread, but that's only logarithmic in the system size. And so that's kind of the intuition why this might be a fast scrambler. And one can do some kind of semi-classical simulation that in fact shows evidence of that logarithmic time scale if you have 10 to the 4 spins. But actually, if you wanted to look at this in the quantum regime, that's not something you can calculate. It's something that also is hard to simulate experimentally. So there are experimental challenges as well, but hopefully at some point this toolbox can come to the point where you can really start to probe models that you can't calculate in just numerically and ask, is it a fast scrambler? How does it behave in the lab? So if you wanted to probe the scrambling, there are a few different ways to do it that I will say more about actually the rest of today. And roughly speaking, the general approach often is inspired in what I'll talk about today is inspired by kind of our classical notions of like, what does it mean for a system to be highly chaotic? Or how would I detect chaos even classically? So quantum systems are different, but classical intuitions can be useful. And one classical intuition is kind of probe the system, probe how chaotic the system is by asking how sensitive it is to perturbations. And for example, asking the question, if I were to kind of perturb the system and try to undo the effect of that perturbation in a way, I'll be more precise about that later, can I or can I not undo it? So that's kind of one approach, and one of the sort of, I'll just briefly mention sort of one of the key experimental tools that one needs to adopt that approach is the ability to change the sign of the Hamiltonian in order to do something where you sort of evolve forward in time, but then at some later point evolve back in time to try to undo the evolution. Okay. And so one thing I want to highlight is this is a system where one has actually control of the sign of the interactions. I showed before some pictures with ferromagnetic and with anti-ferromagnetic interactions. That ability to can actually be a useful tool for some methods of probing chaos and scrambling, which I'll say more about in a moment. A second sort of kind of general concept is, again, sort of inspired by classical physics. How sensitive are the dynamics or is the final state of the system to the initial conditions? So one other thing that's useful is being able to compare a range of different initial states in the system. And this is also something where actually in the lab, it's a fairly standard tool for us by now to essentially locally address different sites and perform local operations, which could be used to prepare a very random initial state or a range of different initial states and ask how that affects the evolution. So that's kind of one approach to probing scrambling that has been demonstrated in some other experiments that I'll talk about in a moment. And the last approach has to do with teleportation protocols, and that's something we'll talk about next time. But the basic resource there is having kind of two entangled copies of a system. And this is something where, intriguingly, I mentioned last time that actually dynamics of our system kind of naturally give rise to something where we have 3 internal states, and the +1 state and the -1 state each individually end up in something that looks kind of like a thermal state, but the state of the system as a whole is pure. And so that flavor of quantum state actually also can play a role in some protocols for probing scrambling. And so that's also something we'll mention next time. Okay. Okay, so before I kind of get into probing scrambling, which will be kind of the rest of today, I just wanted to kind of summarize a little bit of what I told you about so far in this particular example of kind of the atomic system with programmable interactions. We have a high degree of control over, again, the graph of interactions, and that opens possibilities for exploring, for example, how does the scrambling depend on the structure of the graph? Can you realize something that scrambles like a black hole? But also, I think this idea of kind of reconstructing this bulk geometry from the spin correlations, we did it in the simple model where we already kind of knew what should happen. But perhaps that could be interesting to apply to a wider range of systems to ask, are there other cases where some natural sort of description in terms of the bulk geometry emerges from the experiment in a regime where you can't calculate. I will briefly just mention that, while I focused on kind of a model inspired by thinking about quantum gravity, we're also kind of interested in, taking this control over the interactions and applying it in other directions, which range from realizing interaction graphs that map to hard optimization problems and asking, can you use the physical system to help solve them, to harnessing the control of the interactions to build entangled states with a specified structure that can have applications, for example, in entanglement sensing. So lots of different directions that this can go that are kind of beyond the scope of this week, but just to put that in context. So I'll pause one more time and ask whether there are questions before I move on to the topic of what exactly do we mean by scrambling and how does one measure it in experiments? Very unfortunate that I can't see your faces. I'll fix this for next time.
Can I ask a quick question?
Yeah, please.
So you mentioned briefly that you also want to study scrambling of a black hole. So can you give us an idea of, what should be your system size if you want to study the scrambling of a black hole?
Well, what should be your system size? So I would say, maybe there's more to this that I'm missing, but I would say that sort of a key aspect that one would like to see is this logarithmic dependence of the time scale on the system size. And seeing a logarithm is hard if your system is small. And so this is why, in some sense, the bigger the better, but having a highly well-controlled, there tends to be a tension between having a system in the lab that is highly well-controlled and also one that is kind of large and scalable. But sort of roughly speaking, kind of, I would say, if I look at sort of if I look at the plot I made earlier, just from theory, right? You want to have, sorry, where was this? You'd like to be able to have something where you can sort of look over orders of magnitude in system size. So kind of like hundreds to 1,000 sites would be nice. I think in our system, kind of making arrays of order 100 sites is something that's natural. Going larger becomes hard. And then for us, the biggest challenge actually is being in a regime where you would have, let's say, a single spin per site and something that's really deeply quantum, as opposed to many atoms per site, which is our current scenario. But there are other physical platforms, and I'll touch on sort of one example later that might be of interest, where the state of the art is really having kind of control of individual atoms in arrays of kind of up to order 10 to the 3. And that's already something where you could start to ask about kind of scaling, and is there a logarithmic scaling? Can you build something that's exactly a black hole in those systems? That's another challenge. Can you build something that has something of the flavor and exhibits fast scrambling behavior? Probably yes. And I'll kind of touch on one proposal for that later. Did that answer the question?
Yes, it did. Thank you.
Yeah. I see faces again. Yeah, question.
I have a question which is probably a derail from the main topic, so feel free to send it to the discussion or something else. I was just curious about how you can build up a thermofield double state. Like I used to see it like built with a Euclidean path integral, but that might be, of course, complicated to use, a complicated definition to apply to an experiment. So I wanted to know, how do you build
so basically, there are a couple of different potential approaches. One thing that I kind of found intriguing is that in this particular spin 1 system that we're studying, the dynamics naturally give rise to something that kind of has actually the structure of a thermofield double state. Let's just, where did, oh, I'm going the wrong way in this. I don't want to. And that just arises from this process. I lost track of where that equation was. from this process where naturally excitations in sort of these two, I call them the kind of the +1 mode and the -1 mode, are generated in pairs. But it's the thermofield double state of a harmonic oscillator. And that is perhaps kind of trivial, right? So then the question is, can you turn that into something more interesting by starting from that state and manipulating it? On the other side, there's kind of the idea of take two independent quantum systems that are prepared identically, let them evolve under the influence of some interaction Hamiltonian, or maybe prepare each of them identically in a low temperature state of some interesting Hamiltonian, and then couple the two systems to each other. And there's some work actually showing that for even kind of a fairly generic kind of coupling between the two systems, one arrives at something that is approximately like a thermofield double state. So there are ways of, so there are ways that have been proposed that involve sort of preparing two identical systems and then letting them interact.
Great, thank you.
Yeah. Other questions? Okay. So also feel free to use the raise hand feature or something if you have questions. Otherwise, okay, let's then do what this slide says, which is discuss techniques for measuring this process of scrambling. So let me first maybe kind of define what we mean. And I'll actually just briefly kind of switch to something I can draw on here. Okay, you can see this, right? Did someone say yes out loud?
Yes.
Yes.
Awesome. Okay. So yeah, okay. So what we mean when we talk about scrambling is the growth of some simple operator, let's say a local operator, over time into something more complex due to the influence of kind of interactions in our quantum many-body system. So the idea is, let's say I have some operator that I call W, which is just a local spin rotation, acts on this site. I can ask the question, what does sort of the time evolved? I have also, let's say, some Hamiltonian, H. This is some interaction Hamiltonian. And over time, as the system evolves under this interaction Hamiltonian, if I think in the Heisenberg picture, my operator W at some later time, right, this is e to the IHT, W naught, e to the minus IHT. This can, in some sense, grow to something that no longer acts just on a single site, but involves kind of complex correlations between many sites in this system. And in fact, generically, we could imagine sort of writing down this operator, W, at some later time t, as some kind of a sum over, if this is a spin chain, I could write it down as some kind of a sum over products of Pauli operators. Let's say alpha will be an index, like X, Y, Z, acting on different sites. N, alpha N. And actually, in particular, let's say that we have three different Pauli operators, X, Y, Z, and by sigma naught, I'll mean the identity. So these alphas are in 0, 1, 2, 3. Okay, and then there'll be some coefficients. N. And the question is basically, so we'll sum over kind of all these Pauli strings. And by kind of the size of the operator, so the size of WT is basically kind of saying, asking typically how many of these alpha j's are not 0, right? So how many different sites are we acting on non-trivially, right? So I start with something that's just local, but I end up with something that involves kind of like long strings of Pauli's acting on different sites. And that's kind of what we mean when we say that the operator has grown more complex, and that the operator is scrambling. So this is really a question about, so measuring this process of scrambling is something about measuring how does a simple operator become more complex. And so actually, maybe I'll quickly ask the question, are there thoughts on sort of how you could access that information or quantify sort of the growth of this operator? I can't see faces. If anyone wants to shout something out, go for it. Otherwise, I'll just keep talking. I'm actually going to switch over to my slides, so you have a moment to shout something out if you would like to, about how you might go about sort of measuring or accessing this idea of this growth of the operator.
Measuring how quickly long distance correlations change.
Yeah, so you want to measure something great. So something about the long distance correlations. Any more sort of specific thoughts on like what type of correlation I should look at or how I should measure these correlations?
Like I assume that you could, like if you flip one of the atoms somewhere, you could measure how long it takes for distant atoms to flip.
Yeah, okay, so how long does like some perturbation maybe propagate to a distant atom? I think it's kind of the intuition that you have. Was that true?
Yeah, more or less.
Okay. Yeah, so I think that this is all in the right spirit. So one way that we can sort of very concretely quantify something about sort of this growth of the operator is to basically ask the question, does this operator W, the time-evolved operator, commute with some local operator at a different location? So the basic idea is, at t equals 0, if W and V are both local operators, then they'll commute with each other, local operators acting on different sites. But over time, this growth of the operator W means that it might fail to commute with some local operator V. Generically, right, if W has spread to involve some operator on site V, it will not commute with the local operators on site V. And so the sort of growth of the commutator between simple operators over time is one way of kind of quantifying this process of scrambling. And so this growth of the commutator, it's fairly easy to convince yourself that if I have W and V as unitary operators, then I can write down sort of the squared magnitude of the commutator. I can re-express that in terms of a function called the out of time order correlation function, which is essentially the expectation value of what I've written down here, WT dagger, V dagger, WTV. Okay, so what does that mean? That sort of looks complicated. The way that I like to think about this is that this correlation function captures something about the overlap between two different quantum states. So it's basically saying I start in some state psi, and I want to compare two different states. One is the state I would make if I apply V, and then evolve in time under my interaction Hamiltonian, and then apply W, and which is to say basically I apply V, and then I apply the Heisenberg operator W. Or let's consider a different state, which is the one I would make if I evolve in time, apply W, and then go back in time and apply V. So the question is basically, what is the overlap between these two quantum states where I apply V and W in the right order, or I apply W first, and then I go back in time and apply V. One way that I like to think about this is kind of the sort of top evolution here is the case where all of the sort of slides in my talk are given in the correct order. And so you understand everything and you're very happy. The bottom evolution is the one where I skip some crucial slide at the beginning, and then I proceed to give the rest of the talk. And way into the talk, I realized, oh, I forgot to tell you this one piece of information and you're confused. And so basically what you want to do is to measure the overlap between kind of the happy you and the confused you. Sort of the longer we evolve through the slide presentation before I correct and give you this information, the more confused you'll be and the smaller that overlap will be. Okay, so that's kind of what's going on in this out of time order correlation function. So either the decay of f, this overlap, or equivalent, that is equivalent to the growth of a commutator, saying that this time evolution has kind of scrambled, has led to growth of this operator W. So if you'd like to be able to kind of measure this in experiments, this kind of, what I've shown here is kind of showing some sort of interferometer. We're interfering two different many-body states. And if you'd like to directly realize this, there are kind of two key sort of tools that you seem to need. One is the ability to evolve both forwards and backwards in time, right? We want to do this thing where we go back in time and apply V, and that requires the ability to switch the sign of the Hamiltonian. And if I have a system where the Hamiltonian consists just of interactions, that means basically switching the sign of the interactions. And then I also need some way of kind of interfering these two many-body states. One approach to doing this that we thought about some years ago together with Brian Swingle and Patrick Hayden was to say, if I had some kind of a control qubit, let's say, that can dictate whether or not this operation V is applied, I could initiate that qubit in a superposition of 0 and 1. Let's say if it's 1, we apply some operation V. Then if it's 0, nothing happens, then we time evolve, apply W, time evolve backwards with the negative version of our Hamiltonian, and then flip the control qubit. And now if we didn't apply V before in sort of the upper branch of this interferometer, we apply it here in the lower branch. And so the basic idea, the neat thing about this type of a protocol is actually just by measuring the control qubit in a suitable basis, one actually directly measures, so the expectation value of, let's say, the Pauli X operator in this control qubit directly reveals this out of time order correlation function. So that, and it's really this idea of sort of measuring the overlap between applying these operators in the two different orders in order to obtain sensitivity to the commutator. Okay, and if you want to sort of watch an operator kind of spread by this method, then you would want V and W to be kind of different local operators. And so that's kind of perhaps the most natural way to think about this. One other thing that that we thought about and that a few experiments have been done with is thinking more about systems where one just has global operators. And there's not as simple a picture of sort of the operator spreading from one place to another, but the same kind of general concept applies, that decay of this correlation function or growth of the commutator between two sort of initially commuting operators captures something about scrambling in the system. So I actually found it useful when I was first learning about this to kind of ask in some simple toy model where I just have globally interacting spins and global operations so that I can visualize the dynamics in some kind of a phase space picture. How should I think about what these operators are measuring? So this is kind of a simple toy model where I have a large spin, or it could be many, it could be many individual spins with all-to-all interactions that act like one large spin. This is something that was sort of long thought about as a model for kind of single particle quantum chaos. It's just a single large spin. And in some kind of phase space picture, you could imagine starting in a simple state that is a spin polarized state. And as a function of time, to make a chaotic system here, one can have some combination of a nonlinear term, which is Sx squared, and some precession. And there's a sort of a paradigmatic model called a kicked top, which is chaotic. And the way that manifests itself in the phase space picture is kind of an initial Gaussian blob spreads out into something that looks very complicated. So you could ask what happens in this picture and the time it takes to spread, in this case, kind of the size of the sphere. If it's n spin half objects that make a total spin of length n halves, the size of the sphere is kind of n times the noise of that Gaussian initial state. And so if the thing evolves chaotically, it will take sort of log n kicks for the thing to cover the whole sphere. And similarly, you would expect this sort of out of time order correlation function between two simple operators to sort of convey that, to capture that in the time it takes to decay. And so one kind of interesting thing one can do in this simple model is ask about the decay of that out of time order correlation function, and compare it, why are we measuring this weird complicated thing that involves, WTV and WT dagger, V dagger, instead of something simpler like I evolve I have some simple operator V, and I ask whether it can be undone by the Heisenberg operator at a later time. How different are those two evolutions? So if I just had a simple time ordered correlation function, I would have a sort of very fast decay that just has to do with how long does it take for time evolution to make the operator sort of different from what it was at t equals 0. But if I measure this out of time order correlation function, this is something that should really give you information about how long does it take for the operator to kind of spread over the entire Hilbert space. And that has a longer decay. And so so it really is sort of this more complicated type of correlation function really does give you additional information that captures something about the spreading over the entire Hilbert space. Okay, and in this case, in this simple model, the characteristic timescale seems consistent with something that's kind of log n. This is not a fast scrambler because this is a single particle model. The Hilbert space dimension for sort of n spins in a totally symmetric space is order n, not order 2 to the n. So there's no significance to this log in terms of fast scrambling. It's just saying to spread over this sort of order n dimensional space. If we have something chaotic, it'll take sort of the logarithm of n. And that makes sense, and the out of time order correlation function kind of captures that. So now what's actually been done in experiments? So this kind of kicked off a number of different experiments trying to kind of measure these out of time order correlation functions. One actually was precisely a realization of this kicked top model. There was sort of a clever mapping in the group of Bryce Gadway of a Bose-Einstein condensate onto a kicked top, and they implemented some version of the proposal that I showed you, not precisely this fancy thing with a control qubit. I'll show you in a moment how one can do things that are a little bit simpler, but we're able to kind of, in this model that, you can criticize that this is something I can just solve in Mathematica, nevertheless, sort of actually having the control in an experiment to evolve forwards in time and backwards in time and start to measure these things and see that they agree with some simple, in a simple case that you can calculate, was a really nice demonstration. There have been a few other experiments using systems of trapped ions. Also, the first one I'll show is also with kind of all-to-all interactions where there's a simple phase space picture for thinking about what's happening. And very recently, there's been an experiment with superconducting qubits, really implementing kind of this full qubit controlled interferometer in a rather large system of 53 qubits that I'll also say a little bit about. Let me pause here and ask whether there are questions before I talk about kind of specific experiments.
Could you say what those graphs are displaying for us?
The graphs on this slide?
Yeah, on that slide underneath the superconducting qubits.
I am going to say that, yeah.
Oh, okay, great. Thank you.
On another slide.
Perfect.
So this was just to kind of show the overview. And I should mention nuclear magnetic resonance is another kind of technique that's been used. Other questions at this point? Well, I'll try to answer that question. Let me first, though, before I get to the superconducting qubits, let me give an example of an experiment that was done. This is kind of perhaps one of the first measurements of these out of time order correlation functions. And it was done in a system of trapped ions. This is kind of a order 100 ions that you can see a picture of right here. And the way that they interact is somewhat analogous to what I told you about with photon-mediated interactions between atoms, except in this case, the interactions, there are spin-spin interactions mediated by collective motional modes, so by phonons. And in particular, the center of mass mode in one of these ion crystals can mediate a sort of all-to-all coupling between the spins. And in this example, they're not probing a chaotic system, but they're asking, let's take a system where every spin interacts with every other in terms of some collective spin that's the sum of individual spins. The Hamiltonian, the interaction Hamiltonian is SZ squared. It's a bit like the kick without the top. But anyway, so that's their model. And they ask, can we start to measure these out of time order correlations in the system? And so here's kind of the experiment they did. They initiate all of their spins pointing along the x direction. That's this Gaussian blob here, coherent state. And they time evolve under their Hamiltonian here, this interaction Hamiltonian. And then they apply a rotation, this rotation operator that I call W, the one that we want to see grow. Then they evolve backwards in time. And the last thing they do is essentially detect the spins in the x basis. So they measure the magnetization along x. Okay, so why does this actually sounds a little bit simpler than the protocol I gave before? Why does it work? There's sort of a trick, which is choose which correlation function you measure so that it's easy in the experiment, relatively easy. These are not easy experiments, but let's say relatively easy. Actually, can anyone tell in this protocol I just described? So you're measuring a commutator between operators W at time t and V at time 0. Can anyone tell what operator they chose for V? So again, W is this rotation about the x-axis by some angle phi. What is the operator V? Can anyone tell?
Total angular momentum.
Well, the total angular momentum is conserved actually in this system because they start in a spin polarized state and the Hamiltonian is symmetric with respect to permutations of the spin. So do you really mean total or do you mean in some direction?
I guess in some direction.
Okay, yeah, good. So I'll just, so what they're measuring, so their operator V is actually sigma x of actually any of the spins by symmetry. It doesn't matter which one. And the trick that they're using is because they started in a spin polarized state along x, sigma x acts trivially on the initial state. So when I take this expectation value in that initial state, I can ignore that term. And this out of time order correlation function just ends up looking like the expectation value of sigma x in the state that's evolved under the Heisenberg operator W. And so that's why all they had to do was prepare the state along x, evolve under the Heisenberg operator. And I say all they had to do, but this isn't so easy. They have to perfectly evolve under the Hamiltonian H, perturb the system, and then evolve under minus H. So they need to switch the sign of their interactions and still have everything else be the same, right? And then they detect the magnetization. And when they do this, what they see is something where, so their perturbation, this operator W, their sort of simple operator W is just a rotation by some angle about the x-axis. And they actually measure this as a function of angle, but at any fixed angle, these different colors are different times, and you can kind of see that this correlation function is decaying. So that's one thing you can see. But the other kind of cool thing that they do with this that I like is they also, by looking at this full interference fringe versus the angle versus sort of how large a rotation they perform, they can actually get information about, in some sense, kind of the size of the operator in the sense that if you Fourier decompose these interference fringes, you'll see at later times they kind of have funny wiggles in them. They're not very sinusoidal. And it turns out the higher order Fourier components actually are indicative of coherences that involve flipping m spins, flipping multiple spins at a time. So like some process that flips these 6 gray spins into these 6 black spins. If the operator contains terms like that, that would show up as something with a frequency of that's 6 times higher than if I only have kind of single particle spin flips. And so this is really a way of getting some information about sort of, again, this kind of growth from a simple operator into a more complicated one by looking at this Fourier decomposition. So this is a technique called multiple quantum coherence that actually already had a long history in like nuclear magnetic resonance experiments. This is kind of a nice demonstration of how that connects to this idea of the out of time order correlator. So you can see something about kind of growth of the operator from something simple to something that involves kind of couplings between states that differ by multiple spin flips. It's still not something where we can really talk about spreading in a spatial sense, because this is, again, this kind of all-to-all model. There's no sense of spatial locality. So that would also be interesting. And so I would like to give an example of that, but I will pause and ask whether there are questions before I do that. Okay, I don't hear any immediate questions. So let's look at an example where there's a local model. And this is a very recent experiment from the Google group. And they essentially they can use up to 53 qubits on their processor. And they have some local connections between these qubits. And basically the experiment that they implemented is they implement basically a local quantum circuit in order to sort of mimic, or that's their time evolution. It's not exactly a Hamiltonian, but it's some unitary operation that consists of some nearest neighbor gates and some local unitaries alternating between those. And in order to sort of measure this, out of time order correlation, what they're doing is essentially the protocol that I showed earlier, this kind of an interferometer, where there's a control qubit that dictates whether or not a particular operation, in this case it's a Z rotation, is performed on qubit 1. Then they have their time evolution. They perturb some other qubit with what they call the butterfly operator. This is the W, that what I have been calling W, the thing that we're trying to see grow, right? It's sort of the butterfly flapping its wings, and you want to see whether that turns into a tornado over here in Texas, right? And to probe that, again, you have this last controlled operation on qubit 1, and you basically, by measuring this first qubit, by measuring this control qubit, you essentially perform many body interferometry that tells you whether applying V and W in one order or the other is the same or different. Okay, so so somebody asked, what are these plots showing? So essentially, what they're looking at here is they're varying which qubit they apply this butterfly operator to, right? So they're varying sort of where they have this perturbation that will grow under the influence of interactions. And so the different colors here, let's look at the left plot, the different colors represent different places where that butterfly operator is applied. And they're always using qubit 1 as the other site where they're asking, does this local operation on qubit 1 commute with the time evolved butterfly operator? And so the horizontal axis is time. For them, that's just cycles of some unitary circuit that couples nearest neighbors. And this example is a 1D chain of 20 sites. And you see some things that make sense, that this correlation function for any given curve here, which is a certain pair of 2 sites, it decays versus time, but also it takes longer before it starts to decay the further apart the sites are. And that's because this is a local system where information takes time to propagate from one to the other. The gray curve is if they don't apply any perturbation here, they don't apply this butterfly operator. And in that case, ideally, the measurement result would be 1, but in practice, it's an experiment and there's some imperfections and decoherence. And so they can kind of calibrate out this decoherence by normalizing to what they would get if they do the thing that ideally should be an identity operation. And after calibrating that out, they get the plot on the right, where they can basically see this sort of delayed decay of that correlation function that indicates that the operator has spread from a given site. So let's say, in the most extreme case, 20 sites away, that takes the longest time to decay, because in this local circuit, that's how long it takes for information to propagate. And so this is also kind of showing the idea of what's called a butterfly velocity, a time for the information to propagate is basically set by the distance between these 2 sites and the gate time. Okay, so for the person who asked, what do these plots show? Did I answer that question?
Absolutely, thank you.
Great. So I know we're pretty much out of time. I'll just show one more picture that says they can also do this in 2D. And so in 2D, these are just some kind of images showing the different plots as we move from left to right, or after more and more cycles of their circuit. So that's the time evolution as we move from one plot to another, left to right. And you can kind of see, so sort of more greenish bluish values mean that this correlator has decayed, and you can kind of see that spreading in their two-dimensional circuit. The two different rows are just two different choices of the type of interaction, the type of gate that they have in that circuit. But in both cases, they can really kind of watch this operator spreading in 2D. So I do want to mention one other way of measuring scrambling, but we'll get to that next time. Actually, two other ways. So that don't involve this, this time reversal technique, but use other tricks. So we'll get to that next time. I'll just pause now and ask whether there are questions. Yeah.
Thanks a lot, Monika.
Nice.
Are there questions?
So I'll just briefly say, so next time we'll say how you can measure scrambling using more the idea of sensitivity to initial conditions. So preparing random states and doing some simple measurements that don't involve time reversal. How you can measure scrambling using quantum teleportation. And also there are some connections between those methods to actually ways of measuring entanglement directly in quantum systems. And so that's also something that we will talk about next time. So let's see, I don't see your faces anymore. I will fix, again, I'll fix this connectivity thing for next time.
Probably we can try and turn videos back on just for the questions. So
yeah.
So because that'll be, yeah. Is there any, what are the prospects of extracting a Lyapunov exponent? Is that impossible?
No, it's not impossible. So extracting, yeah, so what are the, basically, let me think about this for a second. So the Lyapunov exponent, so I guess the way I think about this kind of measuring scrambling is that the scrambling time is going to be longer than the Lyapunov exponent in general. So the Lyapunov exponent is related to just the time scale for local observables to equilibrate, and then the scrambling time basically says, given that characteristic time scale, how long does it take the operator to sort of spread over the entire Hilbert space? And so the Lyapunov exponent is actually given by a simpler type of measurement. In the example I showed before of like the sort of simple example I gave at the top, for example, this time or the simple time ordered correlation function that already gives you, did I say that correctly? So you can already get information about the Lyapunov exponent just by doing something like evolve the system, apply a small perturbation, and then ask, can you undo that perturbation by evolving back in time? So that's kind of that's known as the Loschmidt echo. That's just a, actually, maybe I even have it's not super important. I had some kind of a slide showing some sort of a Loschmidt echo. Yes, this is the concept. Evolve in time, perturb a little bit, ask whether if you apply minus h, you come back to the initial state. That already tells you something about the Lyapunov exponent. And there were some kind of classic experiments looking even just in like nuclear magnetic resonance at this type of a measurement to say something about, kind of chaos in quantum systems. And so then what you really want to do is kind of compare the scrambling time, which is given by the more complicated out of time order correlation function, with this 1 over the sort of the Lyapunov time, right? 1 over the Lyapunov exponent. And those two things together tell you something about kind of like, is it a fast scrambler? So does that make sense?
I guess it's just that the picture, the plots that I've seen, it seems hard to fit it to an exponential and actually extract a number, or
yeah, that's a good question. And I don't know whether I don't remember these experiments doing that.
Yeah, I guess, okay.
I think the challenge often has to do with system size again, right? Because you kind of want to see something, you want to see some exponential growth, but you only have so much dynamic range, right? So the question is, can you fit that well or not? But at least that's the concept. Yeah. Yeah, it's a good question of what I should look actually back, and it's a good question. Did any of these actually look at the Lyapunov exponent? The only ones that might have So one of the ones I showed wasn't the chaotic system. But yeah, in something like this one with where you see the butterfly velocity, you're saying, can I also say something about what the Lyapunov exponent is?
Yeah.
Yeah. And roughly, it's basically kind of set. You would expect it to be set in something like this random circuit, actually. It's really kind of just set by the gate time.
Okay.
Right. It's really just set by the gate time. So there are kind of two types of systems you might think about. One where, yeah, it's a circuit and it's set by the gate time, or equivalently kind of maybe it's a Hamiltonian, but it's initiated at some high energy density, sort of roughly an infinite temperature state. And then it's kind of set by the characteristic scale of interactions. Or you have a low temperature state, and then you expect it to be set by the temperature, right? And so there's some expectations you could already have for how it should behave, but being able to verify that would, of course, be nice.
Yeah.
Okay.
More questions?
Okay. So if not, next time we'll go into some other ways of measuring scrambling, how you might build fast scramblers, and then also connections to measuring entanglement.
Okay, let's thank Monika again. Thank you. And the next we'll meet on Gather for lunch at 1:30 local time.
Okay. See you all.
Okay. Thanks, Monika.